Okay, so here's the video that I promised you. I'll first look at how many sig figs are here. So this is a pretty straightforward exercise. First thing I'm going to look at is I'm going to say, well, the 2 and the 3 are significant because they're non-zeros. This 0 is between two sig figs, so that makes it significant, so there are 3 here. So let's look at B. Again, non-zeros are significant. I got to look at these zeros, and I say, okay, these are leading zeros, so these are not significant. So then I still have 3. And we'll do a similar thing over here. 4, 7, 1. I've got 3 leading zeros, so I've got 3 sig figs. So again, 1 and 5 are non-zeros, they're significant. The 2 zeros are between sig figs, so they're significant, so we have 4. And then we look at this one. So I got my 5, so non-zero, significant. Now the question I ask myself, these are trailing zeros, but is there any decimal? There's no decimal, so these are not significant. So I ignore all of these as significant digits. I mean, they mean something, but they're just not significant digits in terms of precision. And so that means I've got 1 sig fig. So then, again, 1 is a non-zero. This 0 is a trailing 0 after a decimal, so that's significant, so I've got 2. 3 is non-zero. This is a trailing 0 after the decimal place, and I've got two zeros between those, so I have a total of 4 sig figs. 8 and 9 are significant. These are leading zeros, so they're not, so we have 2. I have 1 and 5. This is a leading 0, so it's not, but these 2 are between sig figs, so they're significant, so we've got 4. I've got 1 is a non-zero, that's significant. There's a trailing 0, that's significant. This is between sig figs, so that's significant. And these are leading zeros, so they're not, so we have 3. K is 1 sig fig for the 2, the non-zero. I've got a trailing 0 after a decimal, and I've got a 0 between, so I've got 3. I've got a non-zero. These are trailing zeros but no decimal, so they're not significant, and I have 1. So again, 2, 3, 5, 1, 8, always significant. Non-zeros are always significant. The 0 is between sig figs, so I've got a total of 6 sig figs here. 2, 3, trailing 0. These are leading zeros, so they're not, and this 0 is between, so it is. So we've got 4 sig figs. 1 and 5 are significant. These 2 zeros are between, so we've got a total of 4 sig figs over here. And 8 and 6, I've got the decimal trailing 0. These are leading zeros, so they are not significant, and I've got 3 for this one. 4, 3 are significant because they're non-zeros. Trailing 0 is significant. A 0 between sig figs is significant, and leading zeros are not, so we have 4. 1 and 1 because they're non-zeros. And then all of these, irrespective of where the decimal is, they're between sig figs, so they're all significant. So I have a total of 5 sig figs here. And then 23, looks like 23 million. So I've got my 2 and 3 are significant. These are trailing zeros without a decimal, so they're not significant. So I have a total of 2 sig figs. Now 2.050, 0550, 2, the 5 and the 5 are sig figs because they're non-zeros. Trailing 0 after a decimal is significant, and this one's between sig figs, so we've got a total of 5. So that's a pretty straightforward thing. So let's move on to the conversions. And what I'm going to do, you're going to see at the end of this video, or at the end of this worksheet, I'm going to add some more conversions back and forth, because I should have redone this worksheet. But let's go through this worksheet. So we want to write this in scientific notation. So scientific notation always has a mantissa that has a non-zero digit followed by a decimal, and then I'll call these significant digits. So any significant digits that follow the 0 are there. That's what we call our mantissa. That's the mantissa of our number. And then we have the exponent. This is the sort of the term escapes me for a second, but it'll come back to me. But then we're going to have our power over here, so 10 to the power of a number. That's our order of magnitude, sorry. That's the term that escaped me for a second there. So we first look at this and we say, look at this mantissa. Does this satisfy this requirement? We have a non-zero followed by a decimal and followed by any significant digits. And it does. 7.080 is already a valid mantissa for scientific notation. And then we have times 10 to the power of minus 7 centimeters. And if you wanted to leave this in centimeters, this was already in scientific notation. However, one thing that you can also recognize is that centi is just times 10 to the power of minus 2. So really, you've got 7.8080 times 10 to the power of minus 7 times 10 to the power of minus 2 meters. So if we combine these, 10 to the power of minus 7 times 10 to the power of minus 2, we take the same base and we add these exponents, right? These two exponents get added together. And so that's times 10 to the power of minus 9 meters. So you could write it, you could leave it as 10 to the way it was in scientific notation, provided you're using centimeters. But if you recognize that centi is a multiplier, like an order of magnitude multiplier, then you can combine that with this and get it into scientific notation. The reality is, notice the sig figs don't change, right? This is 7 is significant, 8 is significant because they're non-zeros. This is a trailing 0 after a decimal, and this is a 0 in between, so we have 4 sig figs. So that's how we would sort of interpret that. This one here actually is in scientific notation. I've got a non-zero followed by a decimal, and then a 0, a trailing 0 after the decimal is significant. So this is already in scientific notation. So you would just write 4.0 times 10 to the power of minus 4 joules. And then we look at the sig figs. We've got one non-zero. We've got a trailing 0 after the decimal, so that's another one. So we have 2 sig figs over here. Now this one gets a little bit trickier. So we've got 500, but this one doesn't satisfy this mantissa notation. It's got to be a non-zero followed by a decimal followed by significant digits. So first let's take a look at this. We've got 500. Just on its own, 500, I've got this would be significant, but these are trailing zeros without a decimal, so they're not significant. So I'm not going to worry about those in terms of significant digits. So my mantissa is only going to be 5, right? But 500 is really 5 times 10 to the power of 2. So 5 times 10 to the power of 2 times 10 to the power of 15. We do the same thing that we did before. These two bases to the base 10, these exponents to the base 10. 10 to the power of 2 times 10 to the power of 15. What we do is we add these exponents together. So this will be 5 times 10 to the power of 2 plus 15 will be 17. So 10 to the power of 17. And then the units are Newton meters. Don't worry, you don't have to worry so much about the units yet. We'll get to what these units mean. Right now, just whenever you write a measurement, write the unit. The unit is an important part of any measurement because it determines what it is that we measured and how we measured it. But for now, you just write the units. You can worry about what those matter at a later point. So again, we look at our mantissa. I've only got one digit, so this would be 1 sig fig. And similar thing over here. So we look at this. We want to have this mantissa written in that standard format. So I'm going to have my first non-zero is the 4. I'm going to have a decimal. I'm going to be followed with the 5. And then the question I want to ask is this 0 significant? Well, this 0 is because it's a trailing 0 after a decimal. So if it's significant, we're going to write that in our mantissa. But 4.50 and 0.00450 are not the same number. This 0.00450 is 4.50 times 10 to the power of minus 1, 2, 3. So I'm 3 to the left, so it's going to be times 10 to the power of minus 3. But that 10 to the power of minus 3 times 10 to the power of minus 10, again, I add these exponents. So negative 3 plus negative 10 becomes 10 to the power of minus 13. And then my unit is just seconds. So now I can look at this mantissa, count the sig figs. This is significant, that's significant, that's significant. So I have 3. The 0 is significant. Again, we wrote it because it was significant in the original measurement. Okay, so we start to look at this. I've got 1.080. So the question is, so this looks like it's a proper mantissa. I've got a non-zero decimal, and then these digits, we can check if they're significant. This is a trailing 0, so the 1 and the 8 are. Trailing 0 after this, the decimal is significant, and that one's between, so I have 4 sig figs. So I'm going to write them all out, 1.080. And this is times 10 to the power of 12. Well, this is already in scientific notation, times 10 to the power of 12 grams. We don't have any kilograms or milligrams. We don't have any multiplier in front, so we're good there. We don't even have to check the way we did that first one. And then we look at this and we say, well, 1 and 8 are significant. This is significant. That's significant. I've got 4. And then we've got 23,000 times 10 to the power of 10. We'll do the same thing. We want to write this mantissa in our scientific notation. So we want 2 followed by a decimal and the 3. And then the question we want to ask ourselves is are these zeros significant? Well, there's no decimal, and these are trailing zeros, so these are not significant. We're not worried about these in terms of significant digits, so we won't write them in the mantissa. But they have some meaning because 23,000 and 2.3 aren't the same thing. 23,000 is 2.3 times 10 to the power. So if I move the decimal, I go 1, 2, 3, 4 decimal places. That's times 10 to the power of 4. So 10 to the power of 4 times 10 to the power of 10. I'm going to add those exponents. So it's going to be 10 to the power of 14. And then our unit is kilogram meters per second. Sorry about that noise. And then if we consider the sig figs here, we've got 2 and 3 are both non-zero, so they're significant. And so we have 2 sig figs. So I'm going to try and speed things up to do the other stuff because we're already over 10 minutes, like 11 or so. We're going to calculate the density of this cube. So density, of course, is mass over volume. But if I've got a cube, then I've got 3, like all the sides are the same. So it's that's going to equal s cubed. So it's going to be mass over s cubed, which we have the mass, which is 8.02 grams. And I've got 2.1 centimeters all cubed. And that works out to 0.866,0.865999971, something like that. And this will be grams per cubic centimeter. But then what the critical thing here is we're doing sig figs, so we have to look at this and we say that when I'm multiplying numbers, multiplying or dividing, my result can only have as many significant figures as the least significant figures in my measurements. So here I've got 2 sig figs. Here I've got 3 sig figs, so my answer can only have 2. So I'm going to, the 0 is not significant, the 8 and the 6 are, but then I have to look at what's after that, and since that 5, 9, that's closer to 0.87 than it is to 0.86, so we can say therefore the cube's volume, the cube's density is 0.87 grams per cubic centimeter. So that gives, that's the answer. So we just do the calculation as we would normally do. We'll get a number. We'll get a nice long number sometimes. Sometimes it's shorter. But we have to look at our result. Does our result can meet our significant digit rules? So for multiplication and division, it's the least number of sig figs. But if we move on to addition, so here I've got a situation where I'm going to go traveling west. I'm going to go south. I'm going to travel east. And I'm going to travel back north. And notice that this is 2.6 kilometers. This is 1.03. This is 2.6 and 1.03. Well, I'm going to travel as far west as I'm going to travel east. I'm going to end up back where I started. But we want to ask, the distance that we travel is how far we went around that block. So to get our total distance, so I'll call that D, the total distance will be the first distance plus the second distance plus the third distance plus the fourth distance that we travel. So we can start to add these up. So I've got 2.6 kilometers plus 1.03 kilometers. Notice I use the units all the way through, plus 2.6 kilometers again, plus 1.03 kilometers again. And so I'm going to add that up. So 2.6 plus 2.6 is 5.2, 6.2, 7.2. So it'll be 7.26 kilometers. And then now the rule here for addition and subtraction is my result can only be as precise as my least precise measurement. So this is precise to the tenths, this is precise to the hundredths, this is precise to the tenths, and this is precise to the hundredths. So my least precise is to the tenths, so I'm going to be limited to the tenths position. So I've got 7.26. I look at the next digit. So 6 is, the 26 is basically closer to 30 than it is to 20. So we're going to round it up to 7.3. So we'll say, therefore, the total distance is 7.3 kilometers. Okay? And then the last thing that I wanted to do was look at some more examples of converting from between scientific notation and standard notation. So we can convert from scientific to standard notation, or we go from standard to scientific. So let's go both ways. So 4.32 times 10 to the power of 9. So basically all I'm going to do to go from scientific notation, I'll take that mantissa, I'm going to write it, or just write out the digits, and those are all significant digits. And then I'm going to say, well, what this means, the 10 to the power of 9, is since this is positive, that means I'm going to shift my decimal place to the right. So I'm going to, let me do this in red. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places to the right. So I'm going to have to use placeholder zeros to show how big that number is. So that looks like 4,320,000,000 hertz is in our standard notation. Okay. Ignore the red. That's just me showing the placeholders. So in fact, if I do this, I'll get rid of it. Oops. And again. So that would be our number in standard notation. This one here, 1.08 times 10 to the power of minus 7, this is, because that's negative, it's going to move to the left over here. So let me, again, well, since I got to move my decimal to the left, I'm going to write the 108 over here. And again, I'll change it to red. I'm going to go 1, 2, 3, 4, 5, 6, 7 places over here. Now I can start to fill these in. So that's going to be my decimal. I'm going to have 1, 2, 3, 4, 5, 6 over here, and then I'll put 1 over there because typically when a number is less than 1, we put a 0 in front. So we get rid of that, and that's our in standard notation for this one. And of course, the unit is meters. 3.15 times 10 to the power of minus 2. Again, I'm going to do 315. Change my pen to red, and I'm going to move this 2 decimal places over here. So there goes my 0 and my decimal place. I'll put a 0 in front for that. So there's my number, 0.0315. And then again, all the sig figs that I had in my scientific notation should be in my standard notation. And of course, I never forget the units. Okay, so now what if we go from standard notation to scientific notation? Let me zoom down, go down a little bit so I can write on this. So what I'm going to do here is I'm going to take a look at this, and let's look at the sig figs. So 4 and 5 are significant. This is a trailing 0 after the decimal, so that's significant. These are leading zeros, so they're not significant. Right? So I'm going to write my mantissa, 450. So 450, but I always put a decimal place there. But 4.50 and negative and 0.00450 are not the same thing. I've had to move the decimal place. So if I move my decimal place over here to get to this one, I'm going to start here and I'm going to go to 1, 2, 3 decimal places over here. So that means I've gone, I have 10 to the power of minus 3 because it's 3 to the left. And so left is negative. So going to be times 10 to the power of minus 3. And then, of course, my unit is meters. This one here, 90630. So first, let's check the sig figs. So 9, 6, and 3 are significant. This 0 is between sig figs, so it's significant. This one's just a trailing 0 without a decimal, so that's not significant. So my mantissa is going to be 9.063. Okay, and then I look to see, okay, to get to that standard notation, I had to move my decimal place 1, 2, 3, 4 places to the right, so that's going to be positive 4. So my order of magnitude is going to be 10 to the power of 4, and of course my unit is newtons. And this one here, I'm going to look at this because I've put this milliseconds, right? I've made it milliseconds. Milli is just times 10 to the power of minus 3. Right? So I'm going to replace milli with 10 to the power of minus 3, and then I'm going to have this number here. So let's look at the sig figs. 2 and 7 are going to be sig figs, and 0 is not. Right? So I'm going to start my mantissa as 2.7, but 0.27 is going to be 2.7. So that's going to be 2.7. I had to move this 1 over here, so it'd be times 10 to the power of minus 1. All right? So now I've got 2.7 times 10 to the power of minus 1 times 10 to the power of minus 3. I'm going to add these two exponents here to get that order of magnitude. So this will be times 10 to the power of minus 4, and this will be seconds. It won't be milliseconds anymore, because remember, I replaced milli with times 10 to the power of minus 3. So that would be it in seconds. Now, if you kept the unit as milliseconds, you could ignore the 10 to the power of minus 3, and you could just have 2.7 times 10 to the power of minus 1. So I could say, or this is 2.7 times 10 to the power of minus 1 milliseconds. That would be my unit, is milliseconds. And that should be it. If you have any questions, you can post them on the Google Classroom.